All right, in this section, we're going to look a little bit more at complex zeros and the fundamental theorem of algebra. So that fundamental theorem says that every function defined by a polynomial has at least one complex zero. But the thing we need to note about complex zeros is that this includes real roots, because you could certainly have a function that, or sorry, a zero rather, right? Something that is of the form a plus bi, right? Like all complex things, where the b portion is just zero. So if you have the real number 3, you could write that as 3 plus 0 I, and then it looks complex, right? And it's just a real number. So polynomial functions can have only real zeros. We've looked at cases like that before, where everything factors really nicely and we get real numbers for our results. We can have only non-real complex zeros. So that would be something like, something like this, x squared plus 4, something where we don't cross the x-axis at all, so there's no real zeros here. But certainly this function is going to have 2 complex zeros. So those are 2 possibilities. And then the third one is, we've got both real and complex, real and non-real complex zeros. So that might be something where we see a function does cross the axis a few times, right? We've got, in this case, just these 2 zeros. But we know that this is a higher degree polynomial because of all of the bouncing kind of back and forth, right? We know that this is probably some even function, right? The end behavior agrees. Even function, but it's probably something like with a leading term x to the 10th or x to the 8th at least, right? All this bouncing around. So we have a bunch of zeros that are unaccounted for, and so those are probably non-real zeros. All right, so in order to find all of them, we start off like we normally do. We say, well, let's factor this thing. Let's see what we can sort out and get the real factors according to this. But of course, we can also extract some non-real factors. So, right, sometimes we get factors like x minus 2. Then we go, great, I've got a real number solution to that, 2. And then other times we get factors like kind of the one we just called out, x squared plus 4. Now, we can't factor that any further as far as real numbers are concerned, but non-real numbers, so complex numbers, we could factor that a little bit more. So if we have something like this and we're figuring out what makes it 0, right, we can set each of these factors equal to 0 and solve from there. So we've done that for both real numbers and non-real numbers before. So the number of zeros theorem, this is actually a really handy thing. So a polynomial of degree n has n zeros, right? Some of them might be real and some might be non-real, but in total, we should have n total zeros. All right, that means that we could have a complete factorization that is linear. So this breakdown of our polynomial p of x, where it has all of this x minus c1, x minus c2. Okay, well, those c's are just the various zeros of the polynomial. So they might be real, but they might be non-real as well, right? Or some mix. But basically this is saying, yeah, you could just break this down into a bunch of linear factors, right? And we'll consider that, there could be complex zeros going on here. Okay, so let's take a look at an example. So let's find all real and complex, well, so this should really say, just find all complex zeros, but this means real and non-real complex zeros, right? Complex, again, does include the real numbers. So let's take our p of x, and we notice that there are 4 terms here, right? And when we have 4 terms, we're going to factor by grouping. So we're going to factor the first 2 terms together, x cubed minus 3x squared. And we're going to put the third and fourth terms, right, the second 2 terms together. And we're going to say, all right, what do those 2 terms have in common? Well, the first 2 terms have x squared in common. So we get x minus 3. And then we kind of see what we want here, which is that the stuff in the parentheses is the same for both of these. If you want to write a 1 out in front of this x minus 3, sometimes that helps just to remember, hey, there is something here, right? It's not a 0, it's a 1. So since both of these share this x minus 3, then we can factor that out. We can say, okay, this becomes x minus 3. And then we say, what's left over if I factor that out? X squared plus 1. Okay, so we did all the factoring that we could, seemingly, right? And that was our, if we go back just a little bit here, first part, factor the polynomial, if possible. So we got something like this. Set each factor equal to 0. So let's do that part of it. So x minus 3 equals 0. So x is going to be 3. There's one solution. And then x squared plus 1 equals 0. So x squared is equal to -1. Now, here's where we say, okay, you know, real numbers, this is going to be problematic. I can't square something and get a negative. But we know that we're okay dealing with complex numbers. So x is going to be plus or minus the square root of -1. Right? Another way to say that is plus or minus I. Right? We've defined I as the square root of -1. So we have a function, a polynomial of degree 3, right? So we should have 3 total zeros. In this case, one of those zeros is real and 2 of them are non-real, right? So we found all of the zeros for p. Now let's complete the factorization. So p of x, we said, you know, we could factor this thing into x minus 3 and x squared plus 1, right? But that's not a complete factorization. What that means is get it down into all linear factors, right? So everything should look like x plus or minus something. So x minus 3 was that first factor. And then we're going to have 2 more factors. So instead of this quadratic factor, we're going to have 2 linear factors. Keep in mind, this is like our C1. 3 was like our C1, our first 0. So C1 was 3. C2 was positive I, our second 0. And C3, negative I, was our third 0. So when we go for this complete factorization, everything should look like x minus your zeros, right? X minus C1, x minus C2. So let's keep that in mind. Okay, so x minus 3, that was the first one, right? X minus C1. Our next one's going to be x minus I, because that's C2. And then the last one's going to be x minus negative I, so really x plus I. And there's our complete factorization, right? Everything is linear there, and we do have a mix of real and complex. Okay, so another example here, we have a function h. So let's factor this thing into linear and irreducible quadratic factors with real coefficients. So again, this is kind of saying like, don't get into the complex stuff just yet, or anything that has an imaginary component, just stick with what we have so far. Okay, so the first thing we're going to do for h of x is we're going to say, hey, wait a minute, I notice that 3, 24, and 48 are all divisible by 3. So let's factor out that. That's our GCF, right? So our GCF is 3. But hold on, we also have x to the 5th, x cubed, and x. Those all have an x in them. So really our GCF is going to include x as well, right? We could factor that out. And if ever you can do this, absolutely do, right? Simplify things for yourself. So if we take 3x out of the first term, we are still left with x to the 4th. If we take 3x out of the second term, we are left with 8, right? 3 times 8 is 24. And then x squared, x times x squared is x cubed, plus 16, right? 3 times 16 is 48, and then our x is already out front, so we don't need another one there. Okay, we are going to factor this thing a little bit further, right? We're supposed to get linear and then irreducible quadratic factors. So right now we have a linear term, 3x, but then we have a quartic, a 4th power function here. So we say, okay, well, what do we do with that? You could do a couple of things. One thing is to use a similar scenario where you right? We've done u substitution before, where u is x squared. So that means that u squared is x squared squared, or x to the fourth. So the stuff in parentheses here, we could say, oh, that's really u squared plus 8u plus 16. Right, so that u substitution just allows us to reframe this into something we're more familiar with. Hey, this is a quadratic, and I can factor this into u plus 4 times u plus 4. Oh, that's not bad, right? And we say, oh, well, let's just replace this. What was u? It was x squared. So it was x squared plus 4, x squared plus 4. Cool. Well, those are both quadratic factors, and they're irreducible, right? I can't turn them into linear factors at this point. There's no way. If it was x squared minus 4, that's great. Difference of squares we can factor, but unfortunately, sum of squares we can't. But that's okay. This is as far as we needed to go for this part of the problem. So we've got 3x, and then x squared plus 4, x squared plus 4. You can always multiply these back out and verify that we get back to where we were in the previous step. But that's as far as we're going to go here. Let's find all real and complex zeros. Well, this just means we have 3 different factors, right? Set them each equal to 0. So 3x equals 0. Okay, I guess what that means if I divide both sides by 3 is that x is 0. So there's one of our zeros. It's a real 0. Right? Then we take another factor, x squared plus 4 equals 0. So x squared is going to be equal to negative 4 if we pull that over to the other side. So x, we use our square root property, is plus or minus the square root of negative 4, which, right, we know that the square root of 4 is 2, but then the square root of negative 1 is I. So we've gotten a little practice in this from previous sections. If you're not sure how to go from this step to the next, maybe review those previous sections where we did things like the square root of negative numbers. So we get these 2 answers, right, which are non-real, right? So complex numbers fall into real and non-real. And I should just clarify that, right? Non-real, complex. Okay, so right now it looks like we have 3 solutions, right? 3 zeros, but this is a degree 5 polynomial, so we should have 5 of those. So we go to the next factor, we go, oh, wait a minute, x squared plus 4, x squared plus 4. So it turns out these zeros are just going to get used again. So we didn't say anything about unique zeros when we called out the number of zeros theorem, right? The polynomial of degree n has n complex zeros. These are, again, not necessarily unique. So it's okay to have repeated zeros, that's fine. So these are repeated, both of them. So okay, let's factor h completely into linear factors. So we said, okay, well 3x was already factored into a linear factor, but x squared plus 4, we're going to break that down. We're going to say x, something, and x something, plus or minus something, right? So we get x minus 2i, and we get x plus 2i, right, for the first factor. But then that's going to happen again, another x minus 2i and another x plus 2i. And if you want to think about this in terms of, what was our first 0? It was 0. What was our second 0? It was 2i, so x minus c2. What was our third 0? Negative 2i. And then when we go to this last factor, we just sort of repeat. So our fourth 0 looks like our second 0. Our fifth 0 looks like our third 0, right? So we do actually have 5 zeros to this. All right, the conjugate zeros theorem. So if p of x is a polynomial function and it has only real coefficients, if it has only real coefficients, and if some complex number z equals a plus bi is a 0, then so is its conjugate. So what that means is So coming to the bottom here, if 2i, or another way to say that is 0 plus 2i, if that is a 0 of our polynomial, then so is its conjugate, a minus bi. So that would be 0 minus 2i. So that would be another 0 if the initial thing is a 0. Okay, 4 minus I, if that's a 0, then its conjugate, 4 plus I, is going to be a 0. And then if negative 2 plus 5i is a 0, so is negative 2 minus 5i. Right, so that's a pretty handy theorem to have, right? As soon as we have one complex 0, or sorry, 0 of specifically the form a plus bi, then we get to use its conjugate as well. Okay, so let's use that here and try to leverage, or at least leverage it for part of this. So we're gonna find a function. So instead of being given this polynomial function, we're gonna find it, and hopefully we'll find it of least degree, meaning yes, there are other polynomials that might satisfy this, but if there's a degree 4 option, don't give me the degree 6 option. Give me the one of smallest degree with real coefficients. So for starters, we have zeros of -1, +1, and 0. So you could label those if you wanted to. This is like, right, C1 is our first 0, C2 is our second, and C3 is our third. And then the leading coefficient is going to be 3. We can get to that part later. Let's at least start with the generic idea of what our polynomial looks like. So it looks like a times x minus C1, x minus C2, x minus C3, right? And that I'm pulling from, let me go back. So that comes here. So there exists complex numbers, right? Zeros of our function C1, C2, all the way up to Cn. We have 3 zeros, so up to C3, where we can write our polynomial like this, right? The complete factorization. So that's all I'm doing. I'm saying, here's our complete factorization. Cool. But let's actually plug some pieces in, right? What do we know? So let's plug in, we have no idea what a is yet, but let's just use these zeros. So x minus -1, so okay, I guess that's x plus 1. X minus C2, so that's x minus 1. And then x minus C3, well, that's just going to be x. So we could multiply everything through here, and we'll have to satisfy this leading coefficient of 3. And because, spoiler alert, it's not going to be 3 when we first multiply this through. So we could say, okay, let me multiply these two first. So we get x squared. If we're doing foiling, we get minus x for the outside plus x for the inside. Those two are going to cancel out. And then the last terms get us -1. Okay, if we do this a little bit further, so then we get x cubed minus x times a. So I'm going to come over here, kind of carry it on. So a x cubed minus ax. Okay, if the leading term, right, needs to have a coefficient of 3, that means, I guess, a is just going to be equal to 3. Right, to get our last property in there. So what is our function? Right, our polynomial function is going to be 3x cubed minus 3x, because we saw a show up in 2 different places. Okay, so we started with the zeros and then we moved on to whatever else we needed. Okay, in the second part, B, we have zeros of 0 and 4 minus 3i. So we have 2 different zeros here, but what we know from that previous theorem here, the conjugate zeros theorem, is that if you have something in the form a plus bi, if that's a 0, then you get another 0 for free, a minus bi. So let's come back here. Well, 4 minus 3i is a 0. I guess that means so is 4 plus 3i. And then we have this other piece that 0 has a multiplicity of 2. Fine. So our polynomial function, since I already wrote it up here in red, sort of the general form of this thing, we can use that again. I won't rewrite that. The other piece is we don't have any specification on the leading coefficient, so I really don't have to worry about a at all. I can just kind of leave that out and cut to the chase. If I want to put something in for a, that's totally fine, but if we're just going for the simplest polynomial that satisfies this, then just let a be 1, and essentially it goes away then. So okay, x minus our first 0, well, that's x minus 0, or just x. And then we have x minus our next 0, which is 4 minus 3i. Notice that I put parentheses around that because I'm subtracting the whole thing. We're going to have to distribute there. And then x minus our second 0, 4 plus 3i. Okay, so that's set up. We want to clean this up just a little bit in a moment. But notice also that we do want to account for the multiplicity of 2 probably at this stage. So 0 has a multiplicity of 2. All that means is that this factor, x, needs to be squared. Okay, so we've kind of satisfied everything except let's always check the directions, right? Just because you think you're done with a problem, always check like what form do we want it in? So find a function, p of x, we did. Being a polynomial of least degree, okay, we didn't put in extra, squares or cubes, only the one that it told us to with this multiplicity, with real coefficients, that bolded part, right? Right now, I see that I've got, 3i and negative 3i in here. That's not going to cut it. So let's work through this, right? So I would say leave the x squared out front. Let's first distribute. So x minus 4 plus 3i if we distribute the negative, and x minus 4 minus 3i if we distribute. Okay. Again, x squared is just going to hang out up front for a while. Here, we're essentially doing foiling, but for foiling first, outside, inside, last, that's when we have two terms in each set of parentheses. But here we have 3 terms, so we have trinomials. So we just have to make sure every term interacts with every other term. So x has to multiply by everything in the second set of parentheses. So we get x squared minus 4x minus 3 times I times x. Then we go to the negative 4. That has to interact with everything. Okay, negative 4x plus 16 plus 12i. And then we go to the 3i. That has to interact with everything. So 3ix, and then minus 12i, and then, minus 9i squared. Okay, there's a lot going on there. So here's what's going to happen. A ton of this is going to get sorted out. So we have negative 3ix and positive 3ix. So those can go away. We have positive 12i, we have negative 12i. So those can go away. All right, so this is going to clean up, pretty nicely. X squared, minus 4x. So I guess I can do minus 8x. Plus 16, and then negative 9i squared. Negative 9i squared. Well, where have I seen I squared before? I guess that's just negative 1. So negative 9 times negative 1, positive 9. So we're going to say plus 16 from here, and then plus 9 from here. So we're going to get plus 25. Oh, brilliant news. We've got all real coefficients now. The only last thing we want to do is distribute that x squared. So our very final answer, let me just put this maybe in green, just so we're seeing that, okay, we're going to be done. X to the 4th, if we distribute, minus 8x cubed plus 25 x squared. And so this thing is degree 4. Well, we only had 3 zeros. So we'd say, well, where's the 4th one, right? Well, that comes through when 0 has a multiplicity of 2. So it counts twice. So 0 counts for 2 of the zeros. 4 minus 3i is the 3rd one. 4 plus 3i is the 4th one. So that all checks out. Okay. Finally, we're going to kind of have a mix of the ones we just did. So we have a polynomial given to us. We're told one of its zeros. We want to write out the factored form. So there's a couple ways that we could operate through this, right? We have x cubed, so x cubed plus 3x squared plus 2x minus 6. We're going to try to factor this thing out completely. So we could go through in the way that we had done before. We try to factor by grouping because we see we have 4 terms. right? So normally we would say factor by grouping. But we see that we have a 0 of 1, and we've already done all this polynomial long division and synthetic division. So we could say, hey, wait a minute. Let's maybe utilize the fact that we have this 0 of 1. Let's see if maybe some sort of synthetic division works for us. So we put our 0 here, right? And then we put our coefficients, 1, 3, 2, -6. And this is where the toolbox really comes into play, right? Because we could try to factor this thing by grouping. It turns out it's not going to quite work out the way we want it to. So that's why having the 0 of 1 is very helpful. So when we try something, we say, oh, let me try factor by grouping. When it doesn't work, we have to have a second option, right? So if we are feeling comfortable with polynomial division, well, great. Whether it's synthetic or long division, right? So tools in the toolbox is what I'll say. Have resiliency. If you can't figure out a problem, try another method, try something else, because there's a good chance that you'll get something to work. So in this case, we're going to say, okay, cool. Synthetic division. Remember that this is your C, the 0 that was called out. In this case, it's our first 0, so you could call it C1. These are the coefficients, right, of the original function p, and then we pull the first coefficient down. And then what we do is we say, okay, let's multiply these together, 1 times 1, and we're going to put it under the next column. And then we just go down the column. We say, okay, 3 plus 1 is 4. Great. And then we're going to do the next thing, right? 1 times 4. Okay, well, I guess that's going to go in the next column there. We just go down the column. So we get positive 6, right? 2 plus 4 is 6. We do the same thing, 1 times 6. It's getting a little bit busy here, but thankfully we don't have to do much more. That's positive 6. And hey, this is really awesome because we get a remainder of 0, which is what we're hoping for, right? So we had kind of said before, this tells us what q of x is. It tells us that q of x is 1 times x squared, right? Always one power less than what we started with. So 1 times x squared, or just x squared, plus 4x plus 6. And then we have a remainder of 0, which is good because we were told that 1 was a 0. We should have a remainder of nothing left, right? So, okay, so let's write the factored form. So it's x minus 1, right? X minus our first 0. And then we have x squared plus 4x plus 6. And you could try to factor this further, right? You could go through and say, is there any pair of numbers that has a product of 6, right? Meaning we multiply to 6, and a sum of 4. Well, let's think of all the things we can do to multiply to 6, right? We can do 6 and 1. We can do 3 and 2. We could also do -6, -1, -3, -2, but we have a positive sum, so that doesn't work, right? 6 and 1 do not add to 4. 3 and 2 do not add to 4. So, okay, this is another one of those toolbox moments, right? We tried to factor, but factoring didn't work. So we said, all right, well, that's out of here. So the only place we can go, right, if in this situation, if we just wanted to factor things out, it looks like this is probably irreducible, right? Meaning we can't factor it anymore. So we have a linear factor and an irreducible quadratic factor. Quadratic because it's x squared. Okay, so when we go to find all solutions of p of x, and really this should say all solutions of p of x equals 0. A function doesn't have solutions. It has zeros, right? But it doesn't have solutions unless you make it an equation. So set the function equal to 0. Okay, so let's find all solutions to that. So one of them is 1. So we said, okay, the first one was given to us. C1 equals 1. But this is a degree 3 polynomial. There should be 2 more. And those are going to come from this other factor, right? We've got to figure out what makes x squared plus 4x plus 6 equal to 0. We already said factoring doesn't work. So how about the quadratic formula, right? So opposite of b plus or minus square root of b squared minus 4ac, a being 1. And there's a really good chance, it looks like, we're going to get a negative number under here. So -4 plus or minus the square root. So this is 16 minus 24. So definitely we're going to get -8 under there, and then all over 2. So, okay, this looks like, again, there's a couple ways to go about this. We could say -4 plus or minus I root 8 over 2. You can simplify this a little bit more. -4 plus or minus 2I root 2 over 2. This is getting a little bit fancy with your square roots here, but so let's kind of keep it simple for the moment. Let's say, okay, these are my other two zeros, right? So we had our first 0 was 1, and then our second and third zeros are here, right? The plus accounts for one of those zeros, the minus accounts for the other, right? So we say plus or minus, but really we're saying plus and minus, right? Both of those things, C2 and C3 are zeros to this function, right? And yes, we can clean this up. So ultimately, right, this would be a fine form to have it in. The next one would be a fine form to have it in. All of these are divisible by 2, so there's another way to write this even more simplified, which would be -2 plus or minus I root 2. That's sort of the cleanest way to write it, but you know, that takes a lot of simplifying, which is fine. We have those capabilities, but maybe that's not the focus of this problem. All right, so that's the major idea for this lesson.